The aim of this procedure is to collect serial images through a specific region of brain tissue using the focused ion beam and scanning electron microscope. This is accomplished by first sectioning the brain into slices that are stained and then resin embedded. The second step is to cut the region of interest from the embedded brain section and mount it onto a blank resin block. The third step is to trim the resin block with an ultramicrotome and use the ion beam of the microscope to isolate only the region to be imaged. The final step is to serially image a face of the resin block using the ion beam to repeatedly remove thin layers prior to each image being taken. Ultimately, results can be obtained that show serial images through a region of interest. The image series is collected automatically, and the dataset typically has isotropic voxels so that the image structures can be viewed from any angle in the stack.
The main advantage of this technique over existing methods like serial section transmission electron microscopy, it is able to achieve much higher Z resolution, and compared to electron tomography, it's able to image much larger volumes at an optimal resolution for resin-embedded samples.
The procedure begins by dissecting the fixed brain from an anesthetized perfused rat. Embed the brain in warm 5% agarose in a plastic mold. Orient the brain to the correct angle before the agarose sets solid. Mount the agarose block with the brain inside onto a sample holder. Using a vibrotome, slice 80 micron coronal sections. Cut as many sections as are needed to include the region of interest. Next, place the samples in 20 ml glass scintillation vials. Place up to 10 sections per vial. Rinse the samples 3 times for 5 minutes each in 0.1 molar keiko-dilate buffer. Then, stain the samples with 1.5% potassium ferrocyanide and 1% osmium tetroxide in 0.1 molar keiko-dilate buffer for 30 minutes. Continue staining the samples with 1% osmium tetroxide in 0.1 molar keiko-dilate buffer for 30 minutes. Following this, rinse once with double distilled water for 3 minutes. Then, stain with 1% uranyl acetate in double distilled water for 30 minutes. Next, rinse the sections for 5 minutes in double distilled water and then dehydrate them in a graded alcohol series, allowing 2 minutes for each change. The next step is to embed the sections in increasing concentrations of Durcupan resin mixed with alcohol, allowing 30 minutes between changes. Start with 50 to 50 ethanol to resin, then 30 to 70, then 10 to 90. Finally add the sections to 100% resin for 30 minutes. Then replace the medium with 100% fresh Durcupan resin. Agitate slowly for 1 hour on the roller mixer. Following the embedding, use a wooden cocktail stick to place the sections on glass microscope slides that have been previously coated with mold separating agent. Put as many sections onto the slides as possible, but take care not to overcrowd the slides. Make sure an identity label is also placed between the microscope slides. Place the slides in a 65 degrees Celsius oven for 24 hours. The next day, remove the samples from the oven. Gently push a razor blade between the glass microscope slides and remove the resin layer containing the samples from between the slides. Holding the resin layer with your fingers, gently wash the sample under running water to remove any mold separating agent. Place the sample under a dissecting microscope with transmitted illumination. Using a low power objective, mark the region of interest with a fine needle. Use a razor blade to cut a small 3mm by 3mm square around the region of interest. Use acrylic glue to attach the small resin block to the top of a blank resin block. Next, clamp the block into the holder of the ultramicrotome. Looking through the attached stereo microscope, use a razor blade to trim around the region of interest until only a small pyramid of material remains. Cut the edge of the block close to the region of interest at an angle to the block's top surface. Using a glass knife fixed to the ultramicrotome, further trim the block so that the region of interest can be precisely located with respect to the dimensions of the block's surface. Remove the block from the ultramicrotome and place it under a transmitted light microscope. Photograph the region of interest. Use a jeweler's saw to cut the trimmed block away from the remaining resin stub. With carbon paint, stick the sawn-off block onto an SEM sample holder and orient it so that the side to be imaged faces the outermost edge. After the glue has dried, transfer the preparation to a Cressington vacuum evaporation system and coat the block with a thin layer of gold greater than 20 nanometers. The resin-embedded tissue block is now ready to be imaged in the focused ion beam scanning electron microscope. Insert the sample and its holder into the microscope. At low magnification and using secondary electron imaging, orient the block so that the region of interest and the side of the block to be imaged are facing the operator. Orient the block so that the face to be imaged lies parallel to the milling beam. This results in the electron beam being oriented at 54 degrees to this face. Using an ion beam current of 13 to 27 nanoamps at 30 kilovolts, remove a narrow band of resin from the front of the region to be imaged. Next, switch to backscattered imaging mode to view the milled face that overlies the region of interest. Using the light microscopy reference image taken earlier and the image of the milled face, locate the exact region on the block to be milled and imaged. Using the gas injection system of the microscope, deposit a protective layer around 1 micron thick of carbon or metal onto the surface of the block above the region of interest. Using a current of 700 picoamps, finely mill the region of the block within which the final images will be taken. Allow the milling beam to completely mill this image face until no milling artifacts can be seen on the face. Select the microscope parameters for serial imaging of the face. Typical parameters are voltages between 1.2 to 2 kilovolts with pixel sizes between 4 to 20 nanometers. The pixel dwell time should be around 10 microseconds so that the total time to mill the face and acquire one image is below 2 minutes. Let the microscope rest for at least 2 hours for any thermal changes to dissipate. Start the milling and imaging process to acquire serial images through the region of interest. This figure shows the reversed contrast backscattered image of the block face showing the ultrastructure within a region of the rat brain. All membranes are visible as well as large macromolecular structures. This figure is composed of a total of 1,600 images collected at 5 nanometer spacing, resulting in an image stack with isotropic voxels. This stack can be imaged in any plane with the same resolution.
So, after watching this video, you should have a good understanding of how to prepare brain tissue for serial imaging with the focused ion beam scanning electron microscope.